Welcome to our data mining lesson video on evaluating predictive variables and model accuracy in linear regression. In this video, we're going to talk about linear regression. And linear regression is a form of regression where we assume the output variable is a linear function of the input variables as shown above left here. So in this case, our output variable y, we're assuming it is equal to some linear function of our input variables plus some epsilon, which represents irreducible error or error variance in the y that's not captured in our linear regression model. To implement linear regression, we estimate each of those beta values, which are called the beta hats, and we create this function here with the beta hats. And to use that for prediction, we would take any value of x's for a new observation, put them in this formula, and that would give us as an output this y hat, which would be our estimated output. In this video, we're going to talk about variable selection, which is a process of selecting only the variables that are most important. Doing variable selection will improve our linear regression in a couple of ways that matter a lot in data mining. First, when we're doing prediction, good variable selection will improve prediction performance. This makes sense if you think about it. If you have additional variables in there that have no relationship with the output, think of them as just white noise or some random noise, then when you estimate your betas and get your beta hats, they're probably not going to be 0 for those, and then you're going to be introducing some error into your linear regression predictions. So picking the most important or most significant variable is important for prediction for performance. It also improves model interpretability and gives us better statistical inference. Sometimes this is particularly useful when we want to know which input variables are really contributing to our linear regression or are contributing to the value of the output. So let's talk about how to do variable selection. One method using things that we've talked about is to take a model and simply remove any variables that have a high p-score. Remember, p-score represents significance, and when that p-score is low, then we say that variable is significant. Another method for doing variable selection is using the f-test, which means we're going to only choose a model with high f statistic values. And so the f-test is a test where you compare two different statistical models, linear regression models, and when we say model here, we mean a linear regression model with a given set of input variables. So if we're choosing between two different sets of input variables, we're going to choose the set of input variables that gives us a higher value for the f statistic. The f statistic has the formula shown on the screen here. Right here, and n is the number of observations, and p is the number of predictive variables. And so let's take a look at this f-test and think about what these terms mean. And we're going to do that when we compare it with the r-squared term. Remember, r-squared tells us goodness of fit for a single variable linear regression. F-test, or f-statistic, gives us a goodness of fit measurement for multivariate linear regression. So let's think about what these different terms here mean. So first, on the top of the r-squared, remember from before, TSS is total sum of squares minus RSS. That gives us the explained variance. So we take the total variance present in y, subtract off the residual variance which isn't predicted using our linear regression, and that's explained variance. TSS in the bottom here is just total variance. So r-squared is the proportion of variance in y that's explained by our linear regression. Now let's go over to the f-test, f-statistic. The top portion here, total sum of squares minus residual sum of squares, similar to what we did with the r-squared, that's going to give us the explained variance. Now notice we have a division by y right here. In the r-squared, there's no, division by p. In the r-squared, there's no division by p. That's because p equals 1 when we're doing a single variable linear regression, so we don't need to divide by 1 there. So back over to the f statistic, the top portion is explained variance. The bottom portion is unexplained variance, residual sum of squares. Think of that as the error variance or the unexplained variance. So the f statistic is measuring the ratio of explained variance to unexplained variance. R squared is going to be from 0 to 1, 0 when we don't have a good fit, approaching 1 with better fit. F statistic is going to be 0 basically to infinity, 0 on up. Larger value means you're going to have a larger fit, a better fit. And if you have no relationship between your inputs and your outputs, the explained variance in the top portion would be approximately equal to the unexplained variance in the bottom portion in this fraction, which would give you a value of about 1. And so if there's no relationship between our inputs and our outputs, your F statistic is going to be about 1. And then the larger the F statistic, the better fit, the stronger the relationship between your inputs and your outputs. Okay, so let's talk a little more about model selection. Model selection, remember, means we're selecting the best linear regression model or the best set of input variables. So ideally, we could go through all possible combinations of input variables and find the best one. Best here is in quotes because there's a number of different ways to determine best. One way is through the F statistic, which we just saw, but there are other ways to measure and compare different linear regression models that we're going to talk about in separate videos. The problem with doing this is there's often way too many models to search through. So if we have 30 different input variables, every model corresponds to a different subset of these input variables, and there are going to be 2 to the 30th or somewhere over 1 billion possible models. That tends to be too many for us to search through in reasonable time on a computer. 2 to the 30th is possible. Easily, you can get things that are impossible in any reasonable amount of time to search in a computer. So what we often do is something that's called stepwise search. So we'll take some of our predictor variables and build a model, and then try to grow that model, look through the predictor variables that could be added to make a larger model and compare the F-test for those larger models to the previous one, or look at our current model and subtract off an input variable to get a smaller model and compare that to the previous one. So one of the strategies is, to be a little more specific, you could look at every model that consists of just one input variable, pick the best of those, and then search through adding a different predictor variable to that to grow that into a model that has 2 predictor variables, and continue to grow by adding the next predictor variable that gives you an improvement. But at some point, once your model is big, you might want to try subtracting off some of those predictor variables. And so there's different methods for searching to find the best model. Okay, so let's walk through an example with linear regression with 3 variables. And we're going to look at this model search process and how good variable selection helps us with interpretation. So the data we're going to look at is the advertising data. So the advertising data contains sales in 3 types of advertising for 200 different markets. So in our data mining framework, we have 200 observations. We have 3 dimensions because we have 3 predictor variables or 3 features. The features are, in this first plot, TV. In the second plot, here's radio, and this is the amount of advertising put into TV, the amount of advertising put into radio, and in the last plot, we have the amount of advertising put in the newspaper. You can see fairly clearly just from evaluating these scatter plots with the linear regression, single variable linear regression for each separately plotted, you can see that the TV seems to have a better fit. The radio, there's definitely a positive correlation between the radio and the sales, but the fit may not be as good as the TV advertising. And then newspaper seems to have the weakest relationship between the newspaper amount of newspaper advertising and the sales, but there still is a positive relationship. So let's look at some linear regression models. First, we have here linear regression using sales as our output, and then trying to predict sales based on radio. And so what we have is a fairly large coefficient for the intercept that's in the absence of any radio advertising. What would we expect the sales to be? And then we have our radio advertising, and so we have a 0.2, and so that gives us a positive relationship, positive correlation between radio and sales. The T statistic is 9.92, which is fairly large, and then the p-value is very small. So that tells us that when we look at radio in sales, the radio variable is significant. When we look at newspaper in sales, the coefficient for newspaper is 0.055. Notice that that is smaller than the radio coefficient. So spending money, it seems, on newspaper has less of an impact than radio. But the p-value here is still very small, and the t-statistic is 3. That's like 3 standard deviations. That's not trivial. So the newspaper seems to be, when we do linear regression with newspaper only, a significant variable. Now we do regression on the full model, we get a more complete and more interesting picture. So we see that going through the coefficients first, TV has a positive relationship, so TV advertising influences sales in a positive way. Radio advertising influences sales, a coefficient is 0.189. Something to notice, if we compare that to our single variable model coefficient for radio, single variable we got 0.203. In this multivariate regression we get 0.189. So radio isn't contributing quite as much to sales, but it's only slightly less than it was with the single variable. But the very interesting thing now is the newspaper coefficient is a negative 0.001. So if we looked at this full model only, we would say, oh, newspaper seems to have a negative relationship. If we did a very naive, not very good analysis, we might think, oh, spending money on newspaper causes you to decrease sales. That doesn't really make a lot of sense, and it's bad use of linear regression because I use the phrase cause. Right, so let's go through some of the additional statistics we have here for our linear model. TV has a very high t statistic and appropriately very low p-value. It's so low we say it's significant beyond our normal metrics. Again, radio has a high t statistic and a p-value that tells us it's significant. The particularly interesting thing comes in when we look at the newspaper. At this point, we have a low t statistic and a high p-value. That would tell us we probably want to reject the newspaper as being a significant variable in this linear regression model. And an interesting thing, if you compare the p-value that we just looked at in this multivariate linear regression model to the p-value we got when we did newspaper by itself, when we did linear regression with newspaper by itself, newspaper looks significant. But now when we do newspaper in the presence of also the radio advertising and TV advertising, newspaper becomes not significant. This is probably because the information gained in the newspaper is correlated to information that comes from amount of advertising spent on radio and TV. So we don't need the newspaper amount of advertising in newspaper if we have the other variables present. It's a really good cautionary tale that taking interpretation of a linear regression model when you don't have all your variables or we haven't considered which ones should be included or not included can give you misleading results. So let's talk about the model search process. If we're doing model search on this linear regression model, we only have 3 inputs, so we can do an exhaustive search. So what we have here on the first 3 columns are the 3 input variables, TV, radio, and newspaper. And each row corresponds to a different linear regression model where we've included some subset of the TV, the radio, and the newspaper. So, for example, the first linear regression model is TV only, so no radio, no newspaper. Then our F statistic score is a 312. Remember, a 1 means there's no relationship, or close to 1 means there's likely no relationship between your inputs and outputs. 312 is a fairly significant relationship between inputs and outputs. That's a good, solid F statistic. When we do radio by itself in the next row, we have 98.4. It's not as strong as the TV, which corresponds to what we saw in those scatter plots in the beginning. And then newspaper by itself gives us a 10.9, which is even a weaker relationship between inputs and outputs, but not close to 1. The next model we look at includes TV and radio, and this gives us an F statistic of 859. So I'm going to put 2 stars and an exclamation point because this is the highest F statistic out of all of our different linear models. So if we're going to compare those, and you can compare it to the next 3 rows below, this seems to be the best model, and it consists of the TV and radio. It's important to note that when we do the full model, we still get a fairly high F statistic, 425. So including the newspaper is, while it's lower than an F statistic for the TV and radio model, it's not a terrible F statistic, and it's better than the TV alone. So that still tells us that maybe there's something important that involves that newspaper. And you can spend a lot of time thinking about maybe people spending advertising in newspapers are taking away money from advertising from the other options. Maybe that matters. Maybe it doesn't. Maybe markets where there's advertising in newspaper just corresponds to markets where there's less revenue and less sales, and it's not a cause and effect type of thing. It's just that they happen at the same time. So those are the important things you have to consider when you're trying to interpret linear regression models. But for us, the important thing is this high F statistic for using TV and radio, and this model in this row would be the model that we would probably want to use for prediction, and it's probably the most meaningful model out of our different options. So, okay, so let's review what we've talked about. We've talked about variable selection, which involves removing variables that are not significant or adding variables that are significant. It's often done by choosing models that have a high F statistic, and we'll see other metrics for comparing models and determining how good their fit is. It requires some search. We don't have to search actually through all possible models, but through the set of all possible models. We're going to have to consider some of those, so some subset of all possible models. We've talked about variable selection, that it improves interpretability, ability to do statistical inference, and it improves predictive performance. We've talked about some cautions about inferring causality, and we've talked about cautions with correlated predictors. In our models that we were looking at, the radio advertising and the newspaper tended to be correlated, and so that caused some questions about how we should interpret the newspaper advertising. Thank you very much for watching.